guys, this is my lab 3 for the magnetic field of the bar magnet. So for our introduction, our purpose was to find the distance dependence of the magnetic field due to a small bar magnet, and we would be using an app from the phone. And we would then compare the measurements predicted by the equations for the on and off axis magnetic fields that would be derived from the Biot-Savart law. We would then utilize GlowScript for the visual effects, and we will see that later on in the lab. So for our concepts and principles, we'd be using the Biot-Savart law in general, and we would use this to calculate the magnetic field. This is the first law that is shown underneath the concepts and principles. We would then be using the on-axis form of this law. And as you can see, it's different as it has 2 mu in the numerator as well. We would then be using the distance dependence formula for the magnetic field of the bar, which is K times R raised to the N. So for our experimental setup, we took measurements by downloading our app, which was the Tesla meter. We then placed the phone on the table and rotated it until the X component on the app was 0. And then we would align the meter stick and we would place it on the bottom of the phone in order to run the location from east to west. And then we would locate the magnometer in the phone. We then would have to orient the phone and along a 45-degree angle, and we would plot all of the data that we've obtained into the Excel spreadsheet that we had. And then we would find our on-axis data and our off-axis data that would be, once again, put into the Excel spreadsheet. So then we would have to find a distance where the magnometer would create the magnetic field. And we use different distances for this, as you can see. We also measure the off-axis data, and then we record the Y value of this distance and then move the phone from a distance of d perp. So from the observations that we observed and were able to understand, when the magnometer was far away from our magnet on the opposite end of the meter stick, the magnetic field in the X direction was really close to 0. For me personally, it never actually hit 0, but it was very, very close. The magnometer was close to the magnet. It actually increased the magnetic field in the X direction. And then we also noticed that the Earth acted as if it was a bar magnet as well. So here's the data that we were able to obtain into our GlowScript code. As you can see, for our dperp, our average was about 0.184 meters. And then from the Earth, we have 1.9 times 10 to the negative fifth. And then when we had it measured, it was 3.12 times 10 to the negative fifth. And the way that we got the Y direction corrected of the magnetic field was we would take the measured form and we would subtract it from the Earth form. And that is what we got right there. And we ended up getting that our B net would end up being 4.52, about 4.53 times 10 to the negative fifth. As you look on the graph, you can see that our slope is roughly -3. In our case, it's -2.99, and our y-intercept is at -14.404, and this is going to be coming in handy for our distance dependence formula. So for our calculations to find the distance dependence formula, in the equation, the theoretical n would be -3. From our graph, it is actually our slope, which was -2.9938. So it's relatively close. Using the equation, we can get our k. And so we raise e to the -14.404, which was our y-intercept, and we end up getting 5.552 times 10 to the -7, which would be our k. So then we end up are solving for mu, for the on-axis form of the magnetic field. And in order to do this, we had to assume that our magnetic field on axis would be equal to the b bar that we calculated before. And so we would also set n equal to -3. So this is exactly what we did by doing kr raised to the n is equal to mu naught over 4 pi, which is going to be our constant, 1 times 10 to the -7, times 2 mu over r cubed. And once we plug in our formulas, we get that mu is equal to 2.776 amperes meters squared. So then for our computational model and our GlowScript code, here are screenshots of what the code looked like. In the far left, we have our physical constants, but we also have our k that was derived from the constant and from our y-intercept. We also have the function that defines the dipole with mu and r, and then we also have our distance that would be determined from the origin. Over in the right-hand corner, we have the formulas and the code that will be able to make the arrows that are going to be showing the directions of our magnets and the magnetic field. And then we also have our dperp that was derived and gotten from our experiment. We put that average here in line 90. So here's what the code looks like when it is run. And as you can see here, where it says B at 45 degrees at distance D, in the Y direction, we have 2.52 times 10 to the -5. And if we remember back from our Excel sheet, it was relatively close as it was 4.6 times 10 to the negative fifth. So it's not exactly the same. There is some human error with it, of course, with calculations and everything. It won't be perfect, but it is still relatively close. So for our reflection questions, what if we hadn't oriented our experiment to compensate for magnetic north? Well, our values for our B bar, which we calculated for um, distance dependence, our K, N, and mu, they would all be inaccurate. They wouldn't be the same values that we had calculated before. In addition to that, our magnetic field in the x direction would also be different since it wouldn't be close to zero anymore. And what if we were to stick two identical magnets together? Well, due to superposition, the value for the magnetic field of these two magnets would be greater than the value for one magnet, and it would approximately double. So thank you very much for watching, and here's my glow script.